In the previous lectures, I have discussed the problem of point estimation. In the beginning, when we introduced the problem of statistical inference, we mentioned that there are two broad divisions of this topic. One is where we want to guess the value of a parameter or parametric function. This is called the problem of estimation, and in the estimation we had the problem of point estimation, where we specify a value which we call as an estimator, or sometimes we assign an interval which is called as an interval estimate or a confidence interval. However, there may be situations when we want to test some statement about the parametric function. So, for example, there is a medicine for treatment of a certain disease, and we know that the success rate of this medicine is say 3/4, like 0.75 or 75% of the patients who take this medicine, they get cured. Now, a drug manufacturer introduces an improvisation over this medicine and introduces he wants to introduce the medicine in the market. Now, certainly he will be interested to know whether the new medicine is more effective. Suppose I say P is the proportion of the patients who get cured using this new medicine. Then the question that obviously one has to ask whether P is greater than 0.75. So, now this problem now you can formulate in statistical way in this following fashion. Suppose in general n patients are there, n patients are given the treatment or medicine, and P is the observed proportion, x is the number of patients getting successfully cured using this treatment. Then we can say that x follows binomial n p distribution, and we want to test the hypothesis. We use the notation H for a hypothesis, p is greater than 0.75. Similarly, let me state another problem. Suppose we want to compare the average age at death, that is called longevity, of males in two ethnic populations. In a country. So, let us say there are two ethnic populations. Let me call this population say pi 1 and pi 2, and let mu 1 denote the average age at death in population pi 1, and mu 2 is the average age at death in population pi 2. Then we are interested in testing hypothesis, say whether mu 1 is less than mu 2. We may like to test whether mu 1 is equal to mu 2. We may like to test whether mu 1 is greater than mu 2. We may like to test whether mu 1 is not equal to mu 2. Let me give some names to these hypotheses, say H 1, H 2, H 3, H 4. Now, to put it in the statistical framework, we will assume that the ages at death in the two populations follow certain distribution. We may assume here, so we may assume some distribution for the age at death in pi 1 as say, let me call it f 1 mu 1, and same thing assume in pi 2 you assume as say f 2 mu 2, and then we are testing the hypothesis whether mu 1 is equal to mu 2 or mu 1 less than mu 2 or mu 1 not equal to mu 2, etc. Suppose, so basically what we are doing, what is a statistical hypothesis then? A hypothesis, a statement about the parameters of a population. For example, here I am considering binomial distribution and we are making a statement that p is greater than 0.75. Similarly, here we may be considering two populations, say f 1 and f 2. Of course, we may take them as normal populations or exponential populations or gamma populations, and then we are checking about a statement about the parameters. We are making a statement about the relationship between the parameters here. So, broadly speaking, then we can say that a statistical hypothesis is an assertion about the, actually here we have given the example where we are making a statement about the parameter, but we may also consider something like this. We want to find out the distribution of incomes. So, we may like to check whether the distribution of incomes follows a Pareto distribution or the distribution of the incomes follows some other distribution. So, in that case we are checking the form of the distribution itself. So, in general a statistical hypothesis is an assertion about the probability distribution of population. So, it could be one population, it could be more than one population also. Let us consider, suppose we use two different measuring devices to measure an experimental result. So, some outcome is there from the experiment and we are using two different measuring devices. Now, the results of the two devices may be the same. However, there may be more or less variability in one than the other. So, if we assume that the measurements taken from two devices follow say normal mu sigma 1 square and normal mu sigma 2 square distributions, then we want to test say sigma 1 square is equal to sigma 2 square, or we may like to test say sigma 1 square is not equal to sigma 2 square, or we like to test say whether sigma 1 square is less than sigma 2 square, etc. So, these are statements about the parameters of the distribution. Now, we introduce what is called a null hypothesis. or a composite hypothesis, sorry, alternative hypothesis. Now, in the examples that I have described here, for example, we wanted to check whether the average longevity or average age at death in the two ethnic populations is the same. Now, this statement may not be true, this may be true. Similarly, in the problem of introducing a new medicine in the market for curing a certain disease, we introduced the hypothesis whether p is greater than 0.75. Now, it may be possible that p is greater than 0.75, or it could be that p is less than or equal to 0.75, or we may say p is equal to 0.75, or p is equal to 0.95, or p is equal to 0.9. So, when we make an initial assumption about the probability distribution, that we call as a null hypothesis. So, we may take a decision whether to accept the null hypothesis or to reject the null hypothesis. So, a null hypothesis is the, you can say, tentative or the first specification about the probability model. So, a null hypothesis is a first, or you can say tentative specification about the probability model. So, for example, we may say h p is equal to 0.75, we may say h mu 1 is equal to mu 2, we may say h sigma 1 square is equal to sigma 2 square. So, this is called a null hypothesis. Usual notation in the standard books is used h naught here. Now, when we specify a null hypothesis, we also specify an alternative hypothesis to check that if this null hypothesis is rejected, then what is the other possibility. That specification of another hypothesis in contrast to the null hypothesis, that is called an alternative hypothesis. For example, in this problem we may say p is greater than 0.75, here we may say mu 1 is not equal to mu 2, here we may say sigma 1 square is less than sigma 2 square. So, certainly the general specification can be like this. Suppose we are considering probability model p theta, where theta belongs to a parameter space theta. Then let us consider two subsets, let me call theta naught as a subset of theta and theta 1 as a subset of theta, such that theta naught and theta 1 they are disjoint. Then we may set up the null hypothesis and the alternative hypothesis as. So, this is a problem of testing of hypothesis. For example, in this case your theta naught will become equal to the singleton set 0.75 and theta 1 will become the set 0.75 to 1. In this case, this is the parameter space, here is a two dimensional space, mu 1 is equal to mu 2 is the line. So, the theta naught is this line and all other place this is actually theta 1. In this particular case, we are dealing with the positive half, sigma 1 square is equal to sigma 2 square is this and sigma 1 square less than sigma 2 square is this. So, this is theta naught and this is theta 1. So, the null hypothesis and the alternative hypothesis specify the parameters to be in two distinct parameter spaces. Basically, we are specifying the family here. We can also say if p is the probability distribution, then we can say it belongs to the family p theta, theta belonging to theta naught, or here we can say p belongs to p theta, theta belonging to theta 1. So, the null hypothesis and the alternative hypothesis, they usually divide the parameter space into two complementary regions. Now, the way I have explained here, it is not necessary that the two regions exhaust the full possibility. For example, in this case the union of theta naught and theta 1, that is not the full parameter space. For example, the binomial distribution theta is actually 0 1, but the union of these two is not this. In this particular case, the union will be equal to the full two dimensional space. Once again, in the third problem, the union of these two is only half plane here, half of the first quadrant. So, we may take the null and alternative hypothesis as completely complementary regions, or sometimes they will be only disjoint, but need not be completely complementary. That means, they may not exhaust the full space. Then what is the test of a statistical hypothesis? So, a test of a statistical hypothesis is a procedure to decide whether to accept or reject the null hypothesis. So, usually what we do, we take a random sample, we take observations from the given population, and based on this we take the decision to accept or reject H naught, say. See, for example, consider say a die. Okay. Suppose we are consider a fair die, consider a die, we do not know whether it is fair or not, and consider say p is the probability of occurrence of a 6. Okay. Then we would like to check whether p is equal to 1 by 6 or not. Then we may take a decision based on certain experiment. Suppose we conduct the experiment, we toss the die say a certain number of times, say n times. Okay. Let me put n is equal to some number here, suppose I put 60. Okay. Then we may say that if, and here let x denote the number of 6s. Okay. So, if x is say 9, 10, 11, we accept H naught, and if x is not equal to these numbers, then we accept H 1, or you can say reject H naught. Then this is a test procedure, because what we are doing is based on the sample we are taking a decision whether to accept H naught or to reject H naught. Here I would like to clarify, when we say that we accept H naught or we reject H naught, then these statements do not have the validity of a truth. For example, if I say that x is equal to 9, 10, 11, then we accept H naught. It does not mean that p is equal to 1 by 6. It simply means that based on our test procedure, we are in favor of hypothesis H naught. Similarly, if I observe that x is different from 9, 10 and 11, then we conclude here that H 1 is more plausible. It does not mean that H 1 is actually true. It means that based on the sample, we do not feel that H naught is a correct hypothesis, we feel that H 1 is more plausible. So, acceptance or rejection of a hypothesis based on the sample has only a circumstantial validity. That means, based on the observations, we are making a decision whether to accept or reject a given hypothesis. These are not the assertions about the truthfulness about these hypotheses. Okay. So, that is why this is called only a statistical test or a statistical hypothesis test. Now, the theory that we are going to discuss in the beginning, that is known as the Neyman-Pearson theory of testing of hypothesis. There are some alternating theories also, but I am going to discuss this particular theory here. In this theory, it is essential to specify a null hypothesis and an alternative hypothesis. There are some other approaches where only the hypothesis for which we are initially interested will be enough. Now, the tests have been derived based on certain classification. The simplest classification that is there, that is about a hypothesis which is called a simple hypothesis. So, a hypothesis is called simple, a hypothesis is called simple if it completely specifies a probability model. Let us consider say this problem here. Here if I say p is equal to 1 by 6, then the distribution of x, that is the number of 6s, x follows binomial 60 p. If I say p is equal to 1 by 6, then the distribution becomes completely specified. So, this is actually a simple hypothesis, but if the specification is not complete, then it is known as a alternative hypothesis. For example, if you look at p is not equal to 1 by 6, then this is an alternative hypothesis. Sorry, composite hypothesis. This is known as a composite hypothesis. Otherwise, it is known as composite hypothesis. Let us look at the problems specified earlier. Say, let us consider say x follows normal mu sigma square, where mu and sigma square are unknown. If I specify say h naught mu is equal to mu naught, then this specifies mu, but it does not say anything about sigma naught square. Therefore, this is a composite hypothesis. Suppose I give hypothesis mu is equal to 0, sigma square is equal to 1. Then it specifies completely the distribution here. So, this is a simple hypothesis. We specify what is a test procedure. So, a test procedure I will split into two portions. One of them is called a non-randomized test procedure. So, based on the sample x, we decide to accept or reject h naught. Okay. So, that means a decision rule is nothing but a non-randomized test procedure is nothing but this procedure. So, for example, you may assign a function say dx. So, basically what is happening is that if we have the sample space x, it is subdivided into two regions. One is called the acceptance region and another is called the rejection region. So, this is the acceptance region. I am talking in respect of the hypothesis h naught, acceptance region for h naught, and this is called rejection region. In statistical terminology, this is also called critical region for h naught. That means, a non-randomized test procedure is like this: if x belongs to A, then you say accept h naught. If x belongs to R, we reject h naught. So, this is a non-randomized test procedure. Let me explain through one or two examples here. Let us consider say x following Poisson lambda distribution. Our null hypothesis is say lambda less than or equal to 1 and h 1 is say lambda greater than 1. Now, based on the observations, if x belongs to 0 or 1, then accept h naught, else reject h naught. So, here our acceptance and critical regions are let us also consider another example. Say I have a random sample x 1, x 2, x n from a normal distribution with mean mu and variance 1, and we want to test the hypothesis say mu is equal to say minus 1 against say mu is equal to plus 1. Then we may take a test procedure as reject h naught if x bar is greater than 0, accept h naught if x bar is less than or equal to 0. So, here our acceptance region is minus infinity to 0 and the rejection region is 0 to infinity. Now, when we carry out a test of procedure, a test of hypothesis, so we are basically introducing a decision procedure, whether based on our sample we should accept a null hypothesis or reject the null hypothesis. Since our decision is based on the sample, there are possibility of errors. That means, we might have taken a correct decision, as I mentioned to you that when we say based on our hypothesis procedure that p is equal to say 1 by 6 or p is greater than 0.75 etcetera, it is only an assertion in support of our hypothesis based on the sample. It does not mean that hypothesis is actually true or false. Therefore, because hypothesis involves the unknown parameter of the distribution or the population, which we are not sure what actually the value is. It could be our sample procedure whatever sampling scheme we have employed, based on that whatever sample we have taken, it may be possible that based on that we are taking this decision. Therefore, we are likely to commit two types of errors. They are called type 1 error and type 2 error. So, type 1 error is rejecting H naught when it is actually true, and similarly type 2 error is accepting H naught when it is false. We use the notation alpha as the probability of type 1 error and beta as the probability of type 2 error. Now, the consequences of these two types of errors can be quite different. For example, consider a problem of guessing about, say, the effect of a natural disaster on a certain construction. Okay. Let us say, let say mu denote the effect of, so this could be power, okay, which is measured in power, effect of a natural disaster on a nuclear installation. Now, this effect is estimated in terms of, say, strength. Okay. We may like to check whether mu is less than or equal to a certain specified number. This could be our threshold value, or mu is greater than this threshold value. This is the threshold value. That means, if the strength is below this, strength of the natural disaster is below this, then the damage will not be much. However, if it is above this, there will be, the installation will be demolished. For example, the effect of a tsunami that we observed last year in the Fukushima nuclear plant in Japan. The effect of the disaster was such that it basically demolished the nuclear installation, leading to a very wide catastrophic effect. So, if our hypothesis, for example, null hypothesis is true and we are actually rejecting it, that means we will be making arrangements for a much higher scale of natural disaster. Therefore, we are safe in the sense that even if the natural disaster is occurring, we are safe. However, it may entail a very large amount of expenditure and also the maintenance costs. Whereas, if H naught is actually false and we accept it, in that case we are making a very serious error, as it has happened in the nuclear disaster in Japan. We can consider a much simpler situation. For example, a patient goes to a doctor with certain complaints and certain diagnostic tests are conducted on him. Based on the diagnostic tests, the doctor concludes that the patient does not have the disease. However, actually he may have the disease. If that is so, and the doctor has concluded that the patient does not have the disease, he will not give a commensurate medication, which may lead to further complications to the patient and he may actually ultimately die also. On the other hand, if the doctor concludes that the patient has the disease when actually he does not have the disease, he may give medicines to treat that disease, which may lead to some side effects as well as a financial stress to the patient. So, the consequences of the two types of errors can be quite different, and this probabilities of type 1 error and type 2 error, that is alpha and beta, they give a measure of the size of the errors here that one may have. Let us consider the example that we took earlier. Let us look at the relative values of this. So, consider, say for example, x 1, x 2, x n following normal mu 1, and our null hypothesis say mu is equal to minus half, h 1 mu is equal to say plus half. Now, we take a decision based on x bar, and our x bar, if it is negative. So, we accept the hypothesis, the rejection region is 0 to infinity. So, the decision is based on x bar, that is x bar less than or equal to 0 or x bar greater than 0. Here we accept h naught and here we reject h naught. Now, let us calculate the probabilities here. Alpha, that is the probability of type 1 error, that is equal to probability of rejecting h naught when it is true. That is the probability of the region x bar greater than 0, when it is true means mu is equal to half. Now, here the distribution of x bar is normal mu 1 by n. So, root n x bar minus mu follows normal 0 1. So, when mu is equal to half, when it is true. So, here mu is equal to minus half. So, when mu is equal to minus half, you will get root n x bar plus half, root n x bar plus half greater than root n by 2, that is when mu is equal to minus half. Then this has a standard normal distribution. So, this is equal to probability of z greater than root n by 2. Let us for example take say n is equal to 16. If n is equal to 16, this is probability of z greater than 2, where z follows normal 0 1. The probability of z greater than 2 is 0.0228 if we see the tables of the normal distribution. So, the probability of type 1 error is 0.022, that means it is nearly 2% probability of type 1 error. Now, in this case let us also consider beta. Beta is the probability of type 2 error, that is probability of accepting h naught when it is false, that is equal to probability of x bar less than or equal to 0, when it is false means mu is equal to half, that is when h 1 is true, that is here mu is equal to half here. When mu is equal to half, we have root n x bar minus half as the standard normal variable. Since n is equal to 16, this is becoming 2. So, phi of minus 2, that is 0.0228. So, in this case alpha and beta are same. Now, in ideal test procedure, both alpha and beta should be minimum, basically they should be 0, but practically speaking this is not possible, because if I want to make the probability of type 1 error as 0, that means the rejection region should be an empty set with respect to the distribution when the null hypothesis is true. Now, if the set is empty, then the probability of accepting H naught, that will become almost, actually it will become 1, but if there may be a variation in the null alternative hypothesis value, then it may be very high value. So, simultaneous minimization of, however, simultaneous minimization of both alpha and beta is not possible. In fact, we can try, if we reduce say alpha, then beta will increase, if we reduce beta, then alpha will increase. Let us take, say for example, we modify, consider modified test procedure for the same problem. So, I give the rejection region as say x bar less than minus 1 by 4 and the complementary region, that is the rejection region, as x bar say greater than or equal to minus 1 by 4. If I take this, then our probability of type 1 error x bar greater than or equal to minus 1 by 4, that is equal to probability of root n x bar plus half greater than or equal to root n minus 1 by 4 plus half, that is equal to probability of z greater than or equal to root n by 4, that is equal to phi of minus 1, that is 0.1587. So, you can see here alpha star is greater than alpha. Let us calculate say beta star here, that is the probability of x bar less than minus 1 by 4 when mu is equal to plus half. So, arguing in the same way, this value turns out to be probability of z less than minus 3, that is phi of minus 3, that is 0.0013. So, here beta star is actually less than beta. In fact, this is close to 0.1% actually 0.001. So, here we have drastically reduced beta star, but that has increased alpha, that is the probability of type 1 error. Therefore, one has to look for a compromise solution. The compromise solution is that, therefore, we try to fix an upper bound on one error and then find that test procedure for which the second probability is a minimum. So, a standard convention is to define the hypothesis in such a way that we consider the probability of type 1 error as more serious and then we fix an upper bound to that. So, a standard convention is to fix alpha. So, the example that I have considered here, alpha and beta are two numbers, but in general they will be functions of the parameter. So, if they are the functions of the parameter, then we need to look at the maximum value. So, for example, alpha will be in general a function of the parameter, that is the probability of rejecting H naught when theta belongs to theta naught, that is when it is true. So, we take supremum of alpha theta less than or equal to alpha. This is usually called the size of the test or level of significance. So, let us put this as condition 1, then subject to condition 1, find the test procedure for which beta theta, that is equal to probability of x belonging to acceptance region, that is accepting H naught when it is false, for which this is minimized. Once again, see, minimized means this is a function of the parameter. So, minimized means over theta belonging to theta 1. We also say 1 minus beta theta, that is called the probability of x belonging to R for theta belonging to theta 1 is maximized. This 1 minus beta theta, this is called power function of the test. So, power of the test is defined as 1 minus the probability of type 2 error. So, then we get the concept of most powerful test and the uniformly most powerful test. Thus, if theta 1 is a singleton set, power is a number. So, we can use the notation say beta star phi to denote the power of the test phi, and we maximize beta star phi with respect to phi. This is called so, this gives a test say phi naught, then phi naught is called the most powerful test, that is MP test. If theta 1 is not singleton, then beta phi star theta has to be maximized over theta belonging to theta 1. This will give uniformly most powerful test. So, I mentioned the term Neyman-Pearson theory. So, the Neyman-Pearson theory approaches the testing of hypothesis problem from this viewpoint, that is it solves an optimization problem and gives a solution. So, in the first case they give a simple hypothesis versus simple hypothesis case. So, we are able to get the solution in a standard form, and then those procedures are generalized to obtain the solutions in cases where uniformly most powerful tests can be derived. Let me give example of a power function. Let us consider say x follows say binomial 10 p, and our hypothesis testing problem is say p is equal to 0.6 against say p is equal to say p greater than 0.6. and let us take the test procedure as reject h naught if x bar x is greater than or equal to 7, accept h naught if x is less than or equal to 6. So, here alpha, that is the probability of type 1 error, that is probability of rejecting h naught when it is true, that is equal to sigma 10 c k, k is equal to 7 to 10, 0.6 to the power k, 0.4 to the power 10 minus k. From the tables of the binomial distribution, one can see this value turns out to be 0.382. So, the probability of type 1 error is very high using this test procedure. Let us look at beta, that is the type 2 error. So, that is probability of accepting h naught when it is false. Now, this means p is greater than 0.6 here. This value is simply 10 c k, p to the power k 1 minus p to the power 10 minus k for k is equal to 0 to 6. Here p is any value greater than 0.6. If we consider the power, so this is a function of p here, and if we consider the power, that is beta star p, that is 1 minus beta p, then that is equal to sigma k is equal to 7 to 10, 10 c k, p to the power k 1 minus p to the power 10 minus k for p greater than 0.6. I have tabulated these values for different values of p. You can see it from the tables of the binomial distribution at 0.7, 0.8, 0.9 and 0.95. This value is 0.35. So, this is 0.65, 0.121, 0.879, at 0.9 it is 0.013, this is 0.987 and this is 0.999. So, you can see here that this power function is actually increasing in p, this is increasing in p, actually it is reaching almost 1 as p nears 1. So, that shows that for this, of course, you have the size of the test very high, but even for this size the test is proceeding in the right direction, that is the probability of type 2 error is gradually decreasing and the power function is gradually increasing here. The next point I mention about that we are saying that fix the size of the test alpha and then determine a test procedure for which the power function is maximized. Now, when you say fix alpha, then that is the job of the statistician, that he has to fix alpha, and for that we have to determine a best procedure. The question is what should be the value of alpha. If you look at the standard textbooks here, in the standard textbooks the value of alpha, and even in the questions that they ask, they will fix the values as 0.05, 0.01, 0.1, 0.025, 0.005, etc. So, these are some of the commonly used values which you can find in the tables of the distributions that are used for testing. Now, the reason for taking these values is that in those earlier days the tables of the distributions were calculated manually by using certain computation procedures and then calculators, and therefore, it was convenient to have a few tables, and therefore, the selected values were taken as like 0.05, 0.01. So, basically this means 5%, this means 1%, this means 10%, and slowly these values became like conventional and very standardized, that people generally use these as the level of significance. but there is nothing sacrosanct about these values. In fact, presently it is more fashionable to use what is called as a p value. A p value is the value which will assign. So, basically this is the minimum value of alpha at which we reject a null hypothesis. This is the minimum value at which. So, this is called significance, this is called tests of significance or the p value. We will discuss this procedures a little, afterwards. Firstly, we will discuss the Neyman-Pearson theory, but this is an alternative way of carrying out the test of hypothesis here. Now, in the next lecture, I will give the Neyman-Pearson fundamental lemma, that is the basic result which gives how to find out the most powerful test, and later on we will discuss its applications to various distributional models. So, I will be continuing this in the next lecture.